Hello, let me introduce electronic structure theory to you. I'll do this as a three-part talk. First off, let's talk about what is electronic structure theory. Sometimes this is just called quantum chemistry. Well, let me back up just for a minute and mention that this, as in many other things in chemistry and physics, really is using mathematics to model what's going on. And the philosophy of this goes way back to Plato, at least, where Plato had this philosophy of forms and really thought that the world around us wasn't the ultimate reality, but rather an imperfect copy or shadow of the perfect forms that constituted the best ultimate reality. More recently, 1828, a French philosopher said we can judge the perfection to which a science has arrived by the facility with which it can be submitted to calculation. And certainly quantum chemistry is an area where there are many calculations going on. In fact, at one point, something like 40% of United States Department of Energy supercomputing time was being spent on computational chemistry, including quantum chemistry. Robert Mulliken, in his 1966 Nobel Prize address, said that the era of computing chemists, when hundreds, if not thousands of chemists will go to the computing machine instead of the lab, is already at hand, and there's only one obstacle: somebody has to pay for the computer time. Now, I'm not sure this was literally true in 1966, but it is true now. Thousands of chemists around the world are employed as full-time theoretical and computational chemists, and they use computers every day and don't have labs. So it's true now, even if it wasn't true back in 1966. More recently, in 1998, Nobel Prize was given to John Pople and Walter Kohn. Pople, a very famous quantum chemist, for his development throughout a lifetime career in making new methods in quantum chemistry. And Kohn actually was really a physicist, but nevertheless included in the Nobel Prize in Chemistry because of the importance of his work to chemistry and chemists, for his development of density functional theory, which really became a strong, powerful arm of quantum chemistry in terms of getting decent results very quickly. In 2013, the Nobel Prize in Chemistry was again given for theoretical and computational chemistry for the development of multi-scale models of chemical systems. This award was very interesting because it kind of straddled two areas of theoretical and computational chemistry. These folks who won it, I would categorize more in terms of molecular dynamics type folks, which generally is associated with force fields. But this award also had an element of quantum mechanics in it, in that the award also cites pioneering work in mixed quantum mechanics, molecular mechanics approaches. So let me recap some of the branches of theoretical chemistry before we then move into quantum chemistry. So electronic structure theory, or quantum chemistry, solves for the motions of electrons in molecules. So you're really zooming in on what are the electrons doing. And because it's quantum mechanics, we have to ask what are they doing on average, because it's hard to pin down particular electrons, but that's okay. If you do this, then that'll give you properties of individual molecules as well as potential energy surfaces, and we'll talk a lot more about potential energy surfaces in part 2 of the talk. Dynamics is another area that I'm not really discussing today, but that's the area that solves for the motions of molecules on a potential surface. And you could do molecular dynamics, which frequently entails using force field or classical methods, but you wouldn't have to. In principle, you could do quantum molecular dynamics as well. And this will give you lots of interesting things, including reaction rates and potentially mechanisms. And then finally, statistical mechanics has to do with what happens if you have large numbers of molecules and you're trying to solve for bulk properties like the heat capacity at constant volume or something like that. You can use the techniques of statistical mechanics to take results from quantum mechanics on individual molecules and then extrapolate from that to what the properties of bulk samples of those molecules would be using statistics. Let me briefly compare and contrast quantum versus classical methods. So the quantum methods, if you're talking about atoms and molecules, are going to be more accurate typically, although there can be some exceptions. And then the classical force field type methods are going to be less accurate. The quantum ones tend to give you equations that are a lot more complicated, although I'm going to try to explain what the equations look like and what they mean, and I think you can see that at least setting up the equations isn't so bad. It's the solving them that's the hard part, but the equations themselves are not too hard to understand. The classical methods tend to have less complicated equations, although still sometimes complicated enough that you would certainly want a computer to solve them. Quantum methods typically are very expensive. And by expensive, I don't mean you pay dollars for the equations, but I do mean you pay dollars for the computing time to solve the equation. So sometimes we just say expensive because that's a quicker, easier thing to say. But computationally expensive, or long computation times is what I mean. So maybe you can compute an energy of a molecule, but computing its energy and forces, maybe a billion times, is maybe too hard. So doing dynamics with quantum mechanics is very tricky, but you could do energies and maybe a geometry optimization without a lot of trouble, as long as the molecule isn't too big. Classical methods, on the other hand, are much cheaper and easier to do many calculations. Now, quantum methods are basically required if you are studying the individual properties of what electrons are doing. And so, for example, if you want to model ultraviolet or visible spectra of a molecule, well, that has to do with a molecule absorbing light that comes into it. The photon gets absorbed and disappears. Its energy has to go somewhere. Where does it go? It goes into promoting a quantum leap in the molecule from a lower lying electronic state to a higher lying electronic state. And the colors of light that get absorbed then give you the spectrum of that molecule. And if you wanted to predict all that, you need to know individual details of what are those electrons doing as they hop from one level to another. You simply can't do that with classical methods because they don't know anything about electrons. Similarly, if you wanted to study redox reactions where you transfer electrons, you could maybe try to do it with classical methods if you cooked up a custom classical method that you very painstakingly created to do this just for that purpose. But generally speaking, classical methods don't have an ability to do anything like that because, again, they don't know anything about electrons. They only know about atoms and bonds. Finally, one of the big advantages of quantum mechanics, if you pay for all this computer time, is that you don't need all the empirical parameters that you do in force field methods. So you don't need a bond stretch term or to know what the rest length of each bond is and all of these things. That's totally irrelevant. All you need to know are things like the mass of the electron and what's the value of Planck's constant and things like that, the physical constants. Essentially no or very few parameters. Whereas in classical mechanics you have thousands of parameters that you need for a general method. All right, hopefully that gives you a little bit better idea of when you would use quantum mechanics and when you would use classical force field methods. Now, here's an example of a molecular dynamics simulation that one of my graduate students did some years ago, just for fun or just to try it out. This is actually a quantum dynamic simulation, which I said you normally can't do because the calculations are too expensive. But we did some low-level quantum chemistry calculations. I think these are density functional theory corrected for dispersion, or DFT-D calculations. And it's not a very long molecular dynamic simulation. It's already repeating itself. But you can see here's a benzene dimer floating around in space, and you can see that, well, benzene molecules like each other. They like to associate with each other. It's an attractive interaction. Of course, any molecule likes to associate with another molecule by London dispersion forces. And you can study this and get some details out of it. So that's kind of fun. And these kind of small systems you could do with quantum mechanics, but bigger ones become much more challenging. All right, well, what would you want to use quantum chemistry for? One popular thing to do is to get equilibrium geometries. These can be measured with microwave spectra, so you can get all the bond lengths and all the bond angles in a molecule, at least a small molecule. And you can calculate this very accurately with electronic structure theory, and you can get very good agreement between experiment and theory as long as you're careful about some details that I'm not going to get into. Now, what's an equilibrium geometry? That just means the best geometry, the geometry at the bottom of the potential well. So that's something you can do. Vibrational frequencies, you can calculate those, and that would give you a simulated infrared spectrum of a molecule, and that can match experimental spectra very, very well if you're careful about some of the details. Excited states, I mentioned those a minute ago. You can calculate UV-Vis spectra. That's something you can certainly do with electronic structure theory that you certainly cannot do with classical methods. You can also calculate NMR spectra. This has been a thing for a number of years now, and those can be rather accurate. You calculate circular dichroism spectra. You can calculate dipole moments. You can calculate polarizabilities of molecules. You can calculate barrier heights and reaction paths. Barrier heights just mean that I've got to find what the minimum energy geometry of the system is, and that'll be like the reactant geometry. Then I need a way to carefully go uphill and find the transition state, and I'll say more about potential surfaces in talk number 2. And then that energy difference gives you a barrier height. And by walking around on the potential surface, you can search for what the likely reaction paths would be. If you have that transition state, then you can use transition state theory, or you can do dynamics on the potential surface, either way, to estimate a reaction rate, which is a very useful thing to do. And then if you then go on and do some statistical mechanics, you can estimate thermodynamic properties of a system. So that's obviously useful as well. So there's a lot of things you can do based on electronic structure theory, either direct application of electronic structure theory or an initial application of electronic structure theory, and then subsequent studies maybe with dynamics or statistical mechanics. All right, so in a way, it's very easy to give you a top-level introduction because all I have to introduce is one equation. And that's the Schrödinger equation, H psi equals E psi. Here I'm showing the time-independent Schrödinger equation. For dynamics, I might need to use the time-dependent Schrödinger equation depending on what I'm doing. But H psi equals E psi is the one equation. If I can solve this, I can do a lot. And that's because one of the postulates of quantum mechanics tells me that if I get psi, this wave function, that gives me all the information that is known or even can be known about a molecule. And so from that, I can extract all the properties that I was talking about before, either directly or indirectly by minimizing a geometry or something like that, or mapping out a potential surface. Dirac famously said in 1929 that the underlying physical laws necessary for a mathematical theory of a large part of physics and all of chemistry are known, and the only difficulty is that these equations are hard to solve. And certainly, in terms of the properties of an atom or a molecule, this is the one equation you would need to solve. And if you do this, then you're done. And then you just have to extract what you need out of it, which may be sometimes a little harder than I'm suggesting. But anyway, that is the one equation. If you had a system where the inner electrons were zipping around really fast, close to the speed of light, like a very heavy element like uranium, then in principle the Schrödinger equation might not be enough because it's a non-relativistic equation, and I might need to include relativity, and that would give me something called the Dirac equation. But I'm going to focus on the Schrödinger equation because it's simpler, and also because we can kind of cheat and treat those inner relativistic electrons with a simple potential, and that's sometimes called a relativistic effective core potential, and that then allows us to go back and just use standard HI equals E psi. So let me say a little bit about what this equation means and what it looks like if you're trying to study an atom or a molecule. First off, oh my goodness, this wave function psi, it's just one letter, but it's a function, and it's a complicated function. In fact, it can be complex. If you're a computational chemist, you normally enforce that you're only going to use real functions. But in principle, in quantum mechanics, it's a complex function, so it can have a real part and an imaginary part. And it's a function of many coordinates. What are all these symbols? Well, it depends on the x, y, and z coordinates of electron 1, and also its spin, and I'll borrow this notation from Szabo and Oslin's book, where they pretend there's a sort of a fakey spin coordinate called omega. And so I need the spatial coordinates, x, y, and z, and also a spin coordinate for each electron, and I need it for electron 1 and electron 2 and so on, up to however many electrons I have. And you can imagine if I had 1,000 electrons, I'd need 1,000 times 4 coordinates. And a function of 4,000 coordinates is sort of mind-bogglingly difficult, but that's what it is. So that's one motivation for the development of some alternative approaches like density functional theory, where you work with the density, which is a function of only 3 coordinates, x, y, and z. And maybe you treat alpha spins different than beta spins, so maybe one more coordinate. But that seems a lot simpler than these very high dimensions we're talking about here. But nevertheless, that is what psi is. And let's talk about the Hamiltonian. So I just talked about psi. What about H? So H, or Hamiltonian, is supposed to capture the kinetic energy of all the particles and the potential energy of all the particles. And if I have an atom or molecule, then I know what those are, at least the mathematical functions describing them. So let me show you this cartoon where I'm just kind of laying out a simple molecule. So suppose I have a nucleus with a positive charge Z sub A. So these will be in, let's say, units of the electron charge. If I had hydrogen, this would have +1 charge. But here in this diagram, it could be, whatever. Maybe it's a carbon where it has a +6 charge. That's just the atomic number. It's how many protons it has. And then I've got another nucleus that has some arbitrary charge plus Z sub B. Okay? And these nuclei are separated from each other by a distance RAB. And I'm going to use capital letters for things that pertain to nuclei, and I'm going to use lowercase letters for things that pertain to electrons. Now, any molecule that's not very strange has electrons associated with it. So here's an electron I, here's an electron J, and there's a bunch of distances associated with those. So electron J is at a distance Raj from nucleus A, it's at a distance Rbj from nucleus B, and it's at a distance Rij from nucleus I. So I think you'll see those symbols all make sense. Those are all of the particles in my kind of cartoon molecule with 2 nuclei, 2 electrons, and then that yields all these possible distances. So it's already complicated even if there's only 2 electrons, right? But this is complicated enough that you can see how this would generalize if I had 3 or more electrons or if I had more nuclei. All right. Now, what does the Hamiltonian look like? Well, it always has kinetic energy plus potential energy. This system certainly has kinetic energy and potential energy. And I can imagine what all the basic terms are, even if I don't know the mathematical forms of them. Each nucleus is going to have a kinetic energy, right? Because the molecule might be flying through space. Each electron has a kinetic energy because it's zipping around the molecule. So each particle has a kinetic energy. And then I have potential energies due to all the different kinds of Coulombic interactions between all these charged particles. So the nuclei don't like each other electrostatically because they have positive charges on each of them, and positive charges repel each other. Similarly, the electrons repel each other because they both have negative charges, but an electron is attracted to a nucleus because they have opposite charges, and opposites attract. So those are all the possible kinds of interactions, and then it just remains to write down a mathematical equation that captures all that I just said. And I can do that, and maybe it looks a little scary, but that's what it is. And each term is very easy to understand, and if you know a little quantum mechanics, then the forms of these are actually not so complicated, really. I've got to sum over all the nuclei, and again, capital letters are nuclei, and each nucleus has a kinetic energy, and in quantum mechanics, the kinetic energy is always minus h bar squared over 2 times the mass of the particle, so here it's m sub a, the mass of nucleus A, times del squared with respect to A. So this is just going to be the second derivative with respect to x, y, and z of particle A. And then I have a similar term, and it looks almost identical, except now it's the electrons. So little m here, maybe I should put an E subscript on it. That's the mass of an electron instead of the mass of nucleus A, because here it's electrons I'm summing over. And again, it's minus h bar squared over 2m del squared with respect to whatever particle. Here it's particle I, so it's electron I, and I sum over all the electrons. Then I have all the Coulomb terms, and there's 3 kinds. So one of them is the nuclear electronic attraction. So like this guy here, J is attracted to A because they have opposite charges. And that's just Coulomb's law, the product of the charges divided by 4 pi epsilon naught times the distance. It's negative because the electron is negative and the nucleus is positive. So it's an attractive term. And the product of the charges, well, the charge on the nucleus is just Za, which is an integer, times E. So these are in units of electron charge. And then the charge on an electron just is E. So I get minus Za E times E. So I get that numerator. And then in the denominator, 4 pi epsilon naught times the distance. Great. I mentioned this is negative because it's attractive. These things are also negative on the kinetic energy, but they're repulsive, so why do they have a negative sign? Turns out when you take the second derivative of psi, you'll wind up getting a sign change, and that sign will cancel this negative, and you'll wind up with a positive kinetic energy, which it has to be. Okay. Then there's 2 more terms. What's this one? This is the sum over all unique pairs of nuclei. So here there's only 1 pair, so there'd be 1 term here in this sum. And it's, again, the product of the charges, ZAE times ZBE, or ZAZBE squared, divided by 4 pi epsilon naught times the distance. And then finally, I sum over all unique pairs of electrons, and it's product of the charges divided by 4 pi epsilon naught times the distance. So it's a double sum over I, sum over j, but if I restrict the second summation such that j is less than I, then I'll only count the pairs once instead of twice. I don't want to count anything twice. So if I had electron 1 and electron 2, I want to count, say, the 2-1 term, but not the 1-2 term, because if I did that, I'd have counted it twice. So that's all that's going on in this restricted sum. And there they are: nuclear kinetic energy, electronic kinetic energy, electron nuclear attraction, nuclear repulsion, electron repulsion. So the final 3 terms are potential energies, and the first two terms are kinetic energies. And so at that point, I will stop, and next time we'll talk about part 2, where we'll go into the Born-Oppenheimer approximation and potential energies surfaces.